Good morning, sir. Am I audible?
Yeah, you are audible. I again welcome back participants. We will be having the first session of this online training program on introduction to remote sensing and GIS technologies using QGIS. The first session will be on overview of remote sensing and GIS technologies. It will be delivered by Shri P. Harish, scientist engineer SF grade from National Remote Sensing Center, Department of Space, Hyderabad. He did his MSc in engineering physics with specialization in photonics from NIT Warangal, and he is working as I said, he is working as a scientist engineer in NRSC in the training, planning, and coordination section group. He has a specialization in optical engineering and worked as optical design engineer initially in manufacturing of optical instruments. He joined NRSC in 2010. Currently, he is in the training division, and he has been organizing capacity building programs in geospatial technologies at NRSC, contributing in planning, designing, and structuring the contents and practical tutorials in remote sensing and GIS. His areas of interest are hyperspectral data processing, Earth observations data and applications, digital image processing, geospatial technologies, spatial modeling, and open source tools. Now, I request Shri P. Harish to take over and deliver today's session. Thank you.
Yeah, thank you very much, sir. Thank you, Dr. Chaitanya, for that brief introduction and a very warm, good morning to all the trainee officers joining this particular training program from your own location, from various parts of this country. And as I've heard in this inaugural session that we have a good number of registration for this training program. So that really shows the interest of the young training officers in this particular training program. So once again, my name is Harish, and I'm working as a scientist in National Remote Sensing Center located in Hyderabad. So in the next 1 hour or so, I'll be discussing some your useful concepts related to the remote sensing and the GIS technologies. So I hope I'm audible. My screen share is also visible. So
Yes,
if you
yes.
can confirm, probably we'll go.
Yes.
Yeah, thank you. Okay. Fine then. So remote sensing and GIS technologies, as many of you may be aware, now they have become very commonplace. So in fact, we have heard the chief guest also telling like, now most of the data is available in the public domain, and the software that you are going to use, the QGIS, is also a free and open source software that you can use it without any restrictions. So this shows like how the geospatial technology is opening up to each and everyone. The data is available, the tools are available, the models are available for each of us to basically explore and use them in our own day-to-day activities. So my presentation, of course, being a very basic and a fundamental lecture that gives you an idea of what remote sensing really is and how the GIS combined with remote sensing technology helps us in utilizing the many products and services, the data software that we are getting to see in today's world. So that will be broadly my coverage, and I request all of you to kindly be part of this discussion, be part of this presentation, so that we'll have an interaction also. And you can interrupt me at any time if you have any queries. So you're most welcome to do that, so that we'll try to clarify. So any clarification that probably requires a prolonged discussion, we'll try to put it at the end of the session. So with these few words of introduction, let me again say thank you to the organizers, and also I welcome all the trainee officers of this training program. So broadly, I think you may be already aware. Yeah. So we'll discuss like the two major components in this topic, that is the remote sensing and the GIS technologies. I think it goes without saying like some of the technologies we are already using. For instance, if you see the location-based services or the geotagging applications that are already in use by the general public. So these two examples are nothing but the examples of the remote sensing and GIS technologies. For instance, when you are traveling in a city or in a city that you're not very familiar, your basic reaction would be to see like where this particular place is. Suppose if I have to come to Pune, or some of you have to come to Hyderabad and you have to visit NRSC or NWA Pune, so the very first reaction is to see like how far it is from the airport or the bus stop. So whatever we are making use of is basically the location-based services, which is being developed using the remote sensing and the GIS technologies. And even if we have to book a cab, or let us say order food through our mobile apps, they all use the location-based services in the background, which is nothing but the product of the remote sensing and GIS technologies. And we are also using geotagging, much more now compared to what it was previously. So we can geotag all our assets, our buildings, our our bridges, all the infrastructure that is available in the city. So these are very straightforward examples that we can give of the remote sensing and GIS technologies. But to really understand how these technologies have been developed, we need to probably understand a little bit of science, the technology, the tools, the data. So all these things probably I'll be discussing in the next few minutes of the presentation. So the first question to ask is why we need remote sensing. So although we know about remote sensing and GIS, invariably we are using a lot of data and software tools. The first question to ask ourselves, do we really need remote sensing? And for this question, probably this was answered some few centuries back, and now it is also very relevant, as we can see here, because we are living in a planet that is very dynamic. So we call our planet Earth as a system that is probably, it is comprising of many subsystems, as you can see in the slide. So these are basically the subsystems of a planet Earth. We have the biosphere, the cryosphere, the lithosphere, and the atmosphere. And of course, we have the space that is above the 100 kilometers of the surface. So this is a very dynamic system and keeps on interacting, changing, exchange of energy takes place. And with the climate change looming large and the impacts that we are already seeing, so it is very much relevant for us to understand what state of the condition of the planet Earth is. So that's why we have to do the remote sensing, and it is one of the primary inputs or the data sources that we have here in order to acquire the data. So to understand anything, probably we need to observe it, we need to acquire the data, we need to measure it, we need to model it, we need to understand, and probably then we can will get to know like what exactly is happening on or near the surface of the Earth. So as you can see here, like we are doing, we are acquiring the data through remote sensing. The slide basically shows you like we are acquiring the data about the oceans, we are acquiring the data about the land surface, we are acquiring the data about what how much aerosols we are pumping in the atmosphere. We are also looking at what is the subsurface of the Earth. So all these things probably we are studying through a technique, through a technology or a process called as the remote sensing. So for this, we use the various platforms. I'll be coming to the various platforms also. As you can see here, we are acquiring the satellites are of basically the very efficient means of capturing the data at a very large scale in a very short time. But for any, let us say, emergency applications, we can also fly the aircrafts or the drones to have a quick survey of what is happening, what is the situation on the ground. So we do remote sensing for basically to understand the planet Earth as a system and look at the various aspects of its subsystems. Okay, so the remote sensing is a very simple process. I don't have to really elaborate on the slide that you're seeing here because we have to acquire the data from a satellite platform. Okay, so the space platform, which is around 600 to 800 kilometers above the surface. So here we need to understand a few of the things. Mostly the remote sensing is done in what is known as the visible to the near infrared, and sometimes the short wave infrared portion of the regions. That also includes the thermal region. So why? Because this is probably the what you call the very easiest ways of acquiring the data of the Earth's surface. So what we have is basically the sun that is pumping a lot of solar energy towards the planet Earth. All this radiation basically crosses the atmosphere, falls on the surface, and once this light is getting reflected back, so this is where we put our sensor or the camera on the space platform, right? So this space satellite keeps on orbiting the Earth's surface at, let us say, 600 to 800 kilometers, and it captures the data in a continuous manner. Of course, it has its own what we call structure of capturing the data. We call it as a path and row. And at any point of the time, we can also locate where the satellite is actually capturing the data. So once this data is captured by the sensors of the that are placed in the camera or the what you call the sensor and the satellite, then you can see here, like we have developed. In fact, the NRSC has a mandate of acquiring all the data from our Indian resource satellites, or also the Cartosat series of satellites, and also from some of the foreign satellites. So we have a mandate of acquiring the data of our country here at Shadnagar, Hyderabad. We store the data, we process the data, and we derive various applications out of this data and support various departments, ministries of the government of India for their utilization and benefit. Right. So once this data is captured, you can see here, like it is now what you call downlink to the ground station here. So this is where the data gets dumped. Right. So this is where the data gets transferred, and it actually processes the data, and it is stored in our own network or a storage system. From there, it is basically processed and then made available to the users. Okay, in a way, the remote sensing process, as done from a space platform, is rather simple, as you can see it in the diagram. So this is what is typically called the remote sensing process. Remote sensing, in other words, it is also called as Earth observation. Sometimes you see the word Earth observation, remote sensing being used side by side. But if you go to the context, Earth observation is a more holistic, what you call approach of observing the Earth, whereas remote sensing mainly concerns with capturing the images of the Earth surface, right? So probably this small distinction you can remember. And once the data is made available to the users, now they have to really download the data, then they have to do the interpretation, they have to do some minor what you call image processing, post-processing like georeferencing, radiometric correction, then they have to do the image fusion, all those things. So there are again, a series of techniques the users have to perform in order to make the data ready for deriving the information or extracting the features. Right, so this is basically what the remote sensing process is, but yeah, so a little bit of I'll just, because you're all new to this particular program, I wanted to share like some of the the history or the background of remote sensing. Probably you may be aware, like remote sensing was used as a reconnaissance at the time of the World War. So people who wanted to spy the other nation, what is their artillery, what is their how many soldiers are there. So they use like the spacecrafts with the small cameras, or the pigeons with the small cameras, to spy on the neighboring nations. But as you can see here, like after the World War II, really the need for having a proper observation system at space was understood and realized by many nations, and that is really where the space era started. So it is started from the 1950s. You can see here, like the space age started from during that particular decade. So we had the launch of the very first Earth observing satellite. We had the TIROS, we had the Mercury, Gemini, the Apollo missions, of course, the famous Apollo missions. And then India also slowly picked up its own trajectory of getting into the space domain. We had launched our Aryabhata and Bhaskara missions. So these were mostly for the communication purpose. And probably as the decades passed, we had the growth and the development and the emergence of the India as a new spacefaring nation. So currently, probably we are at the cusp of the expansion of the geospatial industries. So probably we have, in fact, we are very fortunate to see that the data or the tools or the software is now readily available to all of us for making use of it. But this is in just a simple slide showing you how the remote sensing has evolved over a period, and how India was also a part of this the growing domain of remote sensing nations. Okay, then so we have understood why remote sensing is needed. A little bit of like what exactly is the satellite remote sensing. So as I told you, like we are acquiring mostly the images of the surface of the Earth from the remote sensing platform, both in the optical and also in the microwave domain, and little bit also into the thermal domain. So the advantage for having eye in the sky. So that's what it is used as a corollary, like for the remote sensing. So when we have an eye in the sky, it makes our observations rather easier. Okay. So why satellite data is required? Because we can capture the surface, sometimes subsurface, and also the atmospheric content of the Earth from a remote sensing platform on a satellite. Okay, so we have multiple cameras. We have the high resolution cameras. We have the multispectral cameras. We have the thermal cameras. We have what is known as the scanning cameras. So all types of cameras or sensors are available that will basically acquire the data of the surface of the Earth. Not only the surface, what are the constituents of the atmosphere, so of the lands, of the land, the oceans, okay, or forest, or crops, or water bodies. So all basically, once you take an image, whatever is there on the surface is very much visible on the image. Okay, so we can quickly capture this data compared to what we get if we use what you call an aerial platform. So if you do the same capturing from an aerial platform, or let us say a platform relatively less in the height, like your drones or what you call UAVs, still the satellite data capturing holds a lot of advantages compared to other modes of capturing. Right, so we can capture at various spatial temporal scales. Spatial temporal means you can see, like you can capture the data at a very high region. That means you can capture the entire subcontinent data in a single snapshot. You can as well capture the, let us say, the images of the city of Hyderabad or Pune in a single snapshot. Okay, so this is basically the different scales and also the different intervals. Okay, so you can capture at hourly interval, or a let us say 12-hour interval. So every weekly data you can capture, fortnightly data you can capture. That means the frequency of the data capture of the same region is also very much important, especially if you want to do the remote sensing. So that is also very advantageous when we use any remote sensing platform. Okay, right. So once we capture the data, you can see here, you will get a very synoptic view. You will get a bird's eye view of the data that you have captured of the ground. Okay, so compared to, say, other images, you will get to see all the features of the targets that are present on the ground. Okay, so in a single glance, you can see the vegetation, you can see the water bodies, you can see the roads, you can see the buildings. So this type of information, getting in a single snapshot probably is not possible with any other platform compared to the satellite platform. Okay, so you can quickly look at what is happening by just looking at the images, and then if you want to extract some features, extract some information from the satellite imagery, you have the software tools like QGIS, where you can load the data, visualize the data, and then using simple geoprocessing tools, you can extract whatever the information that you want to extract. Right. So the overall objective of satellite remote sensing is basically, as analysts, as decision makers, as scientists, or as researchers, we want to keep track of the what are the changes that are happening on the ground. Okay, and this applies to let us say if you want to do some hydrological modeling, or you want to do some water body mapping, or if you want to see how much is the snow cover and how much water can we predict using the snow cover. So all these things are probably now possible because of the satellite data becoming more and more open to all the users. So they can also estimate probably at a very what you call coarse level how much of information can be extracted from these images. And of course, now you can see here, like we are also understanding what is the impact of our civilization on this planet Earth. So that also needs to be understood. So there are efforts to to understand like how we are basically impacting, like how our civilization is impacting the ecosystem, and what will be the consequences of that in the near future. Okay, so as I've discussed, remote sensing is optical, and also it is called as what you call active. Okay, so optical, basically, if you are using the sun's reflected energy, it becomes a optical or a passive mode of remote sensing. But if you are using, let us say, the pulses of laser, okay, laser, I hope you all understand, or let us say a microwave source of energy, where you are sending the small bursts or pulses of energy towards the Earth's surface, and you're capturing what is known as the reflective or the backscatter of that energy. So in that mode also, we can what you call create images. We can form images of those reflected pulses, and we can create simple imagery form. Of course, with optical, it is much more, it's a well-defined process. It's just like your cameras that you click in your mobile phones or in your other pro cameras. So what you see is basically what you get, okay? But because it is capturing, because the satellite is capturing from, let us say, 800 kilometers in the sky, in the space, then we need to probably ensure like the stabilization of the platform is done, and whatever the energy, or what we call it a signal to noise ratio, is maintained, so that we get a good clarity image from the reflected energy, right? So we'll come to the other parts of the remote sensing also, like what you call the spectrum of energy that we need to use in order to make images out of the reflected energy. But for your information, these are basically the two forms of remote sensing. One is called as an active, or a what you call, where we use an illuminated light source. Passive is basically optical. Okay, so when we say optical remote sensing, it is basically passive remote sensing. If we say active remote sensing, could be microwave, or it could be a lidar, or it could be any other source of energy which is created by the sensor itself, rather than depending on the sun energy or any other source of energy, right? Okay, so this is basically to tell you, like, we have a very big constellation of satellites that are looking at our lands, oceans, weather, climate. Probably yesterday you would have seen, like, we have launched another weather satellite, that is INSAT 3DS. So all these basically form part of a constellation that are continuously looking at the Earth as a system. So this is what we call as a Earth observation satellites, where we have the land, ocean, the atmosphere, and also the weather and the climate-based satellites. So we have our own dedicated series of satellites that are looking at the specific portions of the Earth as a system, and we are getting continuous data about it, and our scientists are continuously working and deriving very useful information. Okay, so a little bit like what do you mean by electromagnetic spectrum, and this is mostly useful if you're beginning to understand the various bands that goes into the multispectral data, or what is the meaning of a panchromatic data, or what is the thermal data, what is the microwave data. So as you can see here, the energy that we get from the sun is continuous. Okay, so it is ranging from very what you call nanometer level wavelength to very to wavelength that extends into kilometers of kilometers, right? So we can see here, like, we are choosing very small portion of this visible spectrum. Not only visible spectrum, it extends into the near infrared, the short infrared, into the microwave region also, so that we can mostly the visible region data is used for what is known as the resource mapping purposes. So if you want to map, let us say, some of the targets of the surface of the Earth, we mostly use some of the visible bands. But if you want to understand this condition of, let us say, some of the features like vegetation, or let us say soil, or our forest, or our water bodies, we may have to look at some of the other regions of this spectrum. That is the near infrared, short wave infrared, and also the thermal region. Okay, so basically it all depends on what kind of study you want to perform using the satellite data. So if your main objective is only for the mapping, probably you may need some of the bands in this visible region, that is red, green, blue. That may be more than enough. But if you want to do some delineation of, let us say, water bodies from the land, you may need the near infrared region. If you want to do some water quality studies, you may have to go for the short wave infrared region. If you want to again go for the water sedimentation studies, you may also need some of the thermal bands. Okay. So which sensor is having what kind of bands, what is the spatial resolution, what is the number of bands it has, okay, how frequently it captures the data. So probably this type of specifications are also need to be understood by the user or the analyst if he is planning to work on the satellite imagery. Okay, and we also have the sensors that capture in the microwave region. So that is what we call it as a synthetic aperture radar. So they have their own system of identifying the frequencies. I'll quickly show you probably just to for you or understanding like how the frequencies or the spectrum is different in the optical compared to the microwave region. Okay. Yeah, so this is probably to tell you like what is the role of atmosphere, because atmosphere is what is protecting the life on Earth. But as you can see here from a remote sensing point of view, it is not that what you call desirable. But although by looking at the composition, that is basically the absorption and the scattering at various wavelengths. Okay, so what you see here on this slide is basically the x-axis is your wavelength, and y-axis like how much of absorption is taking place at each regions of this wavelength. So you can see here like the ultraviolet rays is mostly absorbed by the ozone layer. So then we have the maximum absorption in the blue, green, and the red region. Sorry, this is the transmission. Okay, so you can see here like the transmission is mostly in the blue, green, and the red region. And once it comes to the short wave infrared, you can see here there is a huge gaps in terms of the transmission. So that means these are basically called as the absorption channels, where there is no what you call transmitted energy coming to the surface of the Earth. So we need to basically avoid these zones in order to get a quality data in the satellite image, right? But whereas when it comes to the microwave region, you can see here mostly as you go higher in the wavelength region, mostly the energy becomes transparent. Okay, so that means the energy can penetrate through the clouds, it can penetrate to the atmosphere and reach the surface if you are using the microwave data. So if you use the Ka band or the X band, C band, or the L band of the microwave data, you can penetrate these clouds, you can penetrate the what we call also the aerosols. So you can have imaging during a highly cloudy situation also, which will be useful for our during the times of the disaster or during the monsoon season, especially if you want to make you map the cultivation that is taking place in our country. Okay, right. So the basic takeaway from this slide is the atmosphere does contribute a lot to the attenuation of the signal and also the absorption of the various channels that is contributes basically to the quality of the image that you are going to get in the image. Right, again, so this is little bit of like the electromagnetic waves and spectrum and basically how it is getting absorbed. As you can see here, like this is the ideal black body signature here. But you can see here that the ozone, the oxygen, the water vapor, carbon dioxide basically contribute a lot of absorption and absorption in this spectrum. So what we get at the what you call as the at surface radiance is totally different to what we get at, let us say, the top of the atmosphere radiance. But the other things you get to see in the slide is so we need to understand a little bit of electromagnetic. What is an electromagnetic wave? How it is getting propagated? Like what are its basically the characteristics, properties, and how you keep making use of all these properties and concepts. We will make what is known as the reflectance spectra of different Earth surface materials or the signatures. Okay, so each target, like snow, has its own signature. The vegetation or the crop has its own signature. The soil has its own signature. Water body, in fact, has a very unique signature. Okay, so if you are comparing, let us say, acquiring at a spatial resolution of, let us say, 10 meters, water body has its own signature. So like this, we can derive what is known as the reflectance spectra or the signature of each of the target, and when we can use it for our understanding and the feature extraction from the satellite data. Okay. Yeah. So then if you all put together, this is where the remote sensing technology comes into picture. So we should basically launch satellites to capture the data, right? So then we need to have the infrastructure to receive the data at the ground station. Okay. of course, this is all to, if you are basically, this is what the NRSC does. We basically capture the data. Of course, we send the satellites from our other centers, Sriharikota, and we capture the data at Hyderabad here. And once this data is ready for the users, you can see here, like we need to basically use some of the tools that are provided, either open source or licensed version. Then we need to do a lot of interpretation, a lot of feature extraction, a lot of information extraction from this satellite imagery. You can see here, like this is the satellite imagery in the color image at the bottom, if you see here. So this is basically what is known as the multispectral data, where we have combined the data from different channels like the red, green, blue, and also the NIR channels to make a color composite like this. So you can see here, you see the land portion, you see the water body or the ocean portion in the dark region. In the light blue, this is the most turbid water. All the red pixels, pink pixels are basically your cultivation and also the forest region. You see like a river channel passing through at the what you call the south of this image, and you see a lot of land portions that are bright and some are slightly in the what you call light pink or red color. So this is like what we get if you look at the satellite image of a particular region. So this satellite image we take, we process it, we convert them into maps like this. This is called as a thematic map or a land use land cover map. And we derive a lot of information or applications based on this data, right? So this is one of the examples, like how satellite data is being used for creating what is known as a land use land cover map. And we have done some what we call two cycles of the national land use land cover mapping, especially for the natural resource mapping and management project. And this data is available for the users to look at and also to visualize what are the what you call land use changes, like how the land was utilized, let us say in the past decade of a particular region. Let us say, for example, a Pune or a Hyderabad, how the land was utilized, how the land change has occurred. So probably all these aspects can be visualized, can be modeled, and we can understand a lot of useful outcomes from such a study or an exercise. Okay, right. So this is basically what we are trying to do with the remote sensing data. Okay, and of course the various platforms I've already told you. You have different platforms where we can acquire the remote sensing data. So ideally it should be from the satellite, because that is the only way we can capture what you call the entire information of the surface in a very quick time compared to the other modes of the acquisition, right? So you can use let us say UAVs. Now drones are becoming very popular now. So now they are very versatile, they are very capable, okay, and they can capture, and also the processing also can be done very quickly. So that is now the trend that is happening in the remote sensing domain. But otherwise, previously, especially for scientific weather experiments, we use radio sondes. So we launch, let us say, we'll put a sensor, attach it to a balloon, then we'll fly it, okay, and then this sensor basically captures the information as it flies at different altitudes, and then it beams the data back to the station, and we get the data about like what are the weather parameters. Okay, so this is basically the examples of different remote sensing platforms, right? So what is the platform, what is the altitude, and what kind of observations can be made? So this slide is probably for you to refer and go through and understand. But ultimately, the space platform or the satellite platform is what is desired by many users. Okay, although like for let us say for emergency, or let us say if you want to capture a very high resolution data of a particular region, you can use the UAVs and drones. But ultimately, the satellite platform does offer you a lot of advantages compared to all other platforms. Okay, so this is atmospheric windows, and probably you can see that whatever the numbers you're seeing on the slide are basically the bands of different sensors. Okay, so if you take the sensors of the satellites of the NASA, like the Landsat or the European data, or own multispectral, ISRO's multispectral data, the LIS3, LIS4. So they are basically numbered across the different regions of this spectrum here. And by looking at these band numbers, you'll get to understand like where the spectrum is positioned in this entire electromagnetic spectrum, where the sensor is acquiring the data. Okay, for instance, if you see the thematic mapper at the third one, you can see here it has 1, 2, 3, 4, 5, 7, and 6 bands. Okay, similarly, multispectral. So these are basically the position. That means what is the central wavelength, what is the bandwidth. So if you're trying to understand the what you call the color composition of any camera, you need to basically to understand what is the wavelength in which it is acquiring and what is the center of the wavelength. So this is just to give you like for any multispectral data you take, whether it is NASA or ESA or our own ISRO satellites, basically they have what is known as the bandwidth and also the band center. Okay. So mostly our ISRO satellites are positioned in this 400 to 900 region, 900 nanometer region. And our basic objective with these bands was to do that natural resource mapping, right? And also we have separate weather satellites, we have separate ocean satellites. So that is why we acquire at a very limited region, but these regions are very effective in for the natural resource mapping. Okay, so as I've been telling, like now these technologies have become very commonplace. Now people are talking in terms of the geospatial technologies. The geospatial industry is also given a lot of, it is a booming industry. And in India also, we have a new geospatial policy that is basically looking at how we can enhance these systems so that we can utilize the data better and derive a lot of value addition from this. So this is what our intent also, to see that more and more users basically have the freedom or the liberty to use this data more freely, analyze this data freely, come up with very valuable solutions, so that we all stand to get benefit out of this one. But ultimately, like if you see the spatial technology or the geospatial technology, this is nothing but the it's a combination of remote sensing, geographic information system, and also the navigation system. So navigation basically gives you what is called the position and the timing of a particular object or a target or whatever it is. So navigation system basically are also a part of this geospatial technology that basically combines the information as a readily available location inbuilt in that one, so that we can derive information directly from the data. Okay, so to add a little more to that geospatial information, you can see here now we are also looking at the internet and communication technologies, which are probably now powerful than compared to a decade back. So now we have the 5G with the mobile phones. There are geotagging apps directly available. So you can load this geotagging app and then you can capture a photo of a particular what you call asset or an entity, and then give some brief attribute information of that one. And you can, if you can push it, it basically gets registered as a geotagged what you call entity in a database. Okay. So the information communication technologies with the combination of remote sensing data, GIS, and also the navigation data has now become basically the forerunner in terms of the geospatial technology, right? So once you can combine and develop applications based on this one, it will be a game changer in the coming days. And people are now also talking about the geospatial ecosystem. So this applies to any other probably ecosystem that is also growing parallel to the geospatial technologies. But now, because the information capturing, the processing or the storage, and also the dissemination is probably the very crucial for the real-time applications. Okay, so you can imagine, like if you are using, let us say, if you are trying to book a taxi. Okay, so it all happens real time, right? It all happens real time. You'll get to see like in what time the cab is going to come to your place and in what time you are able to reach the destination. So all these things to happen, basically you need to develop an ecosystem. Okay, so this ecosystem basically gives you a lot of value added information, and that's why you can see here now we are whatever comes into this what you call domain. Now people are trying to make use to bring in that value addition, so that the user gets the benefit out of this one. Okay, so now we are talking about the cloud computing, right? Okay, then there's big data. Of course, now the AI is also coming. The geo AI we are talking about. So we can make use, let us say, 100 years of data, and if you want to process and extract some meaningful information. So if you do it in a very manual mode of analysis, that is not going to work. Okay, so we need to basically think of how to make bring in the machine learning concepts, how to bring in the AI concepts, so that we can extract some useful information. Right, so very quickly, like if you are working in this domain, you need to understand what are satellite images, what are basically its specification in terms of what is its spatial resolution, spectral, and also the what is basically the size of the image. So all these things are called as specifications in a very general term. But you also need to understand like what are the number of bands in that satellite image, what is the pixel size or the spatial resolution. It could be 1 meter, 5 meters, 10 meters, 25 meters, right? And what is the frequency at which is going to capture the data. And if you're working with, let us say, SAR data, probably this is little on the advanced side. You also need to understand like what was the polarization, what you call orientation, whether it is vertical, horizontal, or VVHH. This is just for your information, but probably once you start working, you'll also get to understand all those things. So these are basically the what we call the different ways of looking, different specifications of looking at the data. What is the spectral, spatial, temporal resolution? Right, so spatial resolution basically corresponds to like what is the level of details you are able to capture from the image. Spectral, as I told you, like what are the number of bands that are present in the image, whether it has 4 bands, 10 bands, or if you have more number of bands, then it becomes a hyperspectral data. Then radiometry basically gives you what are the different shades, okay? Whether it's an 8-bit data or a 16-bit data. Now data, mostly the data that you get from a panchromatic data is 16-bit data. So that means that is a very high radiometric resolution. The higher the radiometric resolution, the different shades you can observe in the data. Okay, so if you're looking at the 16-bit data, and if you're observing a water body, and if it is having a lot of sedimentation in the water, probably those shades or those tones can also be visualized directly from the image. So that is the advantage of a radiometric resolution. You'll get to see more tones or shades in the image compared if you look at the very low resolution radiometric resolution data. And temporal resolution is nothing but the frequency at which you're observing the data. And this is especially useful to understand what are the historical changes that have taken place. Okay, so in the 10 years, like if you want to study how the cultivation has progressed, how the city has expanded, how the forests have diminished, how the river course has changed. Probably 10 years, 12 less a time for understanding river course, but you can, if you have the data from, let us say, of the 3 decades or the 4 decades, that data can be pooled together, and we can try to understand like how the changes have taken place over the surface. So all this is possible only if you have the satellite data with you, and the satellite data, you get it only through the technology called as remote sensing. Right, so this is basically a comparison between the multispectral data and hyperspectral data. Multispectral data, as I've told you, this is only used for the mapping purpose. But if you want to quantify, or if you want to do that feature extraction, probably you need a very finer composition of bands called as a hyperspectral data. Okay, so this is again why I'm showing this slide, because especially for the water quality studies and water sedimentation study, hyperspectral data is used. For those of the researchers among you probably want to understand, probably this is the data set that we need to choose if you want to do that water quality. For water mapping, you are very much happy with the multispectral data, right? So this is just a comparison. So some of the slides probably I'll rush through because I need to cover the other portions of this subject also. Right, so this is again for your information. As I told you, our main objective using the ResourceSat series of data was to do the natural resource mapping and monitoring, right? So that's why we went for with the limited number of bands. We have, if you see here, like ISRO has only 5 number of bands, and added to the fact that we already have a separate ocean constellation, separate what we call atmosphere related constellation, weather satellites. So that's why we have a limited number of bands. But these are very useful bands and useful for the mapping and monitoring purpose. Yeah, so this is in a nutshell. Probably, I'm sorry if you're not able to see the top portions. I was trying to close this one, but it's not happening. But this is called as a chain of the remote sensing data acquisition. Okay, so it starts with the data acquisition, right? So this is at our Earth station at Shadnagar. We acquire data from all our a constellation of the ISRO constellation of satellites, and also from some of the foreign satellites. Not only here, we also have a station at Antarctica that basically acquires the data 24/7. And then we do a lot of what is known as the pre-processing that is needed for correcting the data, and the ready-to-use data is made available for the user. Okay, so the user probably, if he is not does not want to go into the details of this, he will get what is a ready-to-use data that he can very well start using the data without waiting for all these correction parameters, right? Yeah. So what we get from the satellite of, let us say, multispectral data, if you are using a list2 data, you'll get different bands like this. And you can see here, like there are different shades in the image. Okay, so you'll see the same land and the water body portions. But as you come across the different images, suddenly the portion that was dark in the first image has now become bright in the fourth image. That is the B4. So this kind of interpixel variation or the intra-pixel variation is what basically allows us to do the feature extraction or the information extraction. Okay, so we can combine these bands, we can interpret these bands, and we can extract useful information. And especially if you are looking at the water bodies, you can see here like water bodies have a very what you call this slow response in the near infrared region. Before, if you see here, there is clear delineation between the land and water. You don't have to really worry about B1, B2, and B3. Just by looking at the near infrared band, you can clearly see this water body and the land segregation. So if you are looking at mapping the water bodies, this is the near infrared band is what we need to target and get the required information. Right. So as I've told you, like this is my satellite imagery. Raw satellite imagery is what we call it. Okay. This is put in a false color composite. FCC means it is a false color composite. We combine multiple bands in a satellite data. We get what is known as a false color composite. This is only done for the visualization. What visualization helps is basically it gives you what is what in the image. Okay. So where are the land, where is the water, where is the vegetation, where are the rivers, where are the linear features. So all this information you get to see if you compose an image from the various bands, that is called as FCC. But we can also derive interesting results out of this band combination by using what is known as the ratios. Okay, so these are called as band ratios. And if you derive what is known as the NDVI, that is the normalized difference vegetation index. Okay, so in short, if you see VI, it's a vegetation index. It will highlight all the vegetation pixels in the image. Okay, so using a simple combination of what you call the near infrared band and the red band in a ratio, you can extract a very in a very single step, right? You can extract all the pixel information directly from the image. This is also possible using the QGIS software. In fact, it is QGIS, it is much more organized. Okay, so if you use the raster calculator in QGIS, in just a single stroke, you will be able to extract this NDVI image without much fuss. Yeah, so once we can also derive the image, and we can do a thorough what you call as a land use land cover classification. Okay, so if you convert any data into a map, it becomes much more easy to read. If you give a satellite image, it is that much more what you call cumbersome. But if you give an image map directly to me, as you can see here, like what are the different land use classes in this image on the right side in a classified image, it is clearly visible. Okay, so I can clearly say where are the forests, where are the agriculture lands, where are the barren lands, where is the shallow water. So this is what we create basically in a QGIS software. We create the NDVIs, we create the classified data, right? And then we combine all these outputs to arrive at a particular result or solve a particular problem. Okay, so this is called as a classified image or a map. Okay, in simple terms, we call it as a map. This is called as a land use land cover map, which is easy to read and categories are available in this particular region. Okay, right. So this is probably again going little higher into this remote sensing, where we also have the hyperspectral data. Because this I'm not going to cover in detail, because what you need to understand is, like, instead of having a very coarse band like what we get in the multispectral data, if we have a hyperspectral data available with us, we can directly use it to extract the information, because these are there are hundreds of bands in a hyperspectral image. They are actually formed, they're stacked together as a image cube. So the more the number of bands, the more the information you can extract. But again, there are a lot of challenges in dealing with this data. So this is again provided for you for just for information. And this is to show you like how hyperspectral is different from the multispectral and the other panchromatic images. Okay, so you have a continuous what you call spacing of the bands very closely, right? So that you get a continuous signature of that particular target, and you are able to extract that target much more what you call convincingly compared to the multispectral or the panchromatic data. Okay, right. So this is what we get from a hyperspectral data here. You can see here the signatures of each and every pixel. That we call it as an image spectra. We can extract it, and we can use, we can have a reference library, and we can compare like how each signature is matching with the reference library. And we can also estimate the proximity of the match, and also if the proximity is within the threshold. Let us say if it is between 90 to 95%, this is, let us say, paddy. Or if it is between 85 to 90%, it is, let us say, what we call wheat. So like this, we can probably establish simple what we call conditions that will help us to classify the each and every pixel. So what we are doing here is not only mapping, we are doing what is known as the feature identification. We are identifying what that particular feature is on the ground. Okay. Right. So this is again a little bit of the spectral signatures. I'll not go into deep into that one. Okay. So this is again a slide showing you the different what you call the imaging spectroradiometers, and how basically there is a trade-off. You don't get to get all the what you call the best specs in any sensor. Okay, especially from a satellite platform, there has to be some trade-off. So if you are going for a high spatial resolution like what we get from the Carlsat 3 or the Iconos or some other high resolution data, there you get a very fine detail of the data, but the footprint is very small. Okay, it is for 10 by 10 kilometers or even further less than that one. Okay. Similarly, if you go for a coarse resolution satellite imaging data, it has basically a wider footprint, but at a very coarser resolution. Okay, so we can capture the data at 200 kilometers, 500 kilometers, even in fact, the entire continent can be acquired as a single footprint, but they do it from a what is called from the meteorological satellites, where the entire Indian region is continuously watched in a single snapshot. Okay. So this is basically to show you what are the trade-offs between the images, radiometers, and also the spectrometers. Okay, right. So this again, I'll not go into this one. Basically, as you get to increase the number of bands, you'll be able to quantify the data better, and that is possible with the hyperspectral data. Right. So then quickly coming to the other form of imaging, this is called as a SAR imaging. So this is what I told you initially, it is called as an active sensor. So you have the passive sensor and you have the active sensor. And this SAR data, SAR sensors use basically the microwave frequencies. Okay. And they try to capture. You will get a typical image out of this as an output. Like how you get an optical image, you'll get a simple typical image as an output, but the entire signal processing is different. So that is where it takes, different what you call signal processing techniques in order to convert that echo or the backscattered into a pixel value. Okay, so that is again based on the magnitude and phase. So again, I'll not go very deep into that one, but the first thing you can appreciate from a SAR image is you can see here, like even if there is a cloud cover, you are able to see the features of the ground. Okay, so because it has the ability to penetrate through the clouds, through the atmosphere, you will be able to see the clear-cut data of the ground even during the cloud cover. Okay, so that's why the SAR data, the primary objective of this data was for the during the cultivation during the monsoon season. It was launched some 15 years back with the main objective of observing the cultivation of the Indian region during the monsoon time. Okay, and now it is also used for the flooding scenarios. If you have a very flood situation in anywhere in the country, if you have a pass on that particular region, you will be able to get to see the cloud-free data of that particular region, right? Right. So this is the cloud optical image. You'll get a lot of cloud. Without optical in a SAR data, you'll see like it clearly is transparent to the cloud. It will penetrate to the cloud, and you can see the terrain of that particular region very clearly in the image. Okay, so this is always called as a side looking, because if you have to increase the what we call the azimuth resolution and also the basically the azimuth resolution is what we increase if it is a side looking radar. So this is basically because to give you some additional slides so that all you're also, aware of this one. Okay, so these are again basically the various frequencies that we use. Mostly we use the C and the L band. Okay, and these are the frequencies, and these are the simple applications. Okay. All right, so this is again because we need to improve the range resolution and also the azimuth resolution. This synthetic aperture radar, SAR, is always side looking. Okay, so this is just for your information, right? And basically the process of acquisition, the processing, and also the image formation is entirely different. Probably that requires a dedicated discussion or a separate training for that one. But the idea is to capture all the echoes, which are actually time stamped, and basically capture those, make a history of that echoes, and then generate the image based on the platform parameters. Like platform parameters means how fast it is moving, and what is the frequency at which the signal has been pulse towards the ground. So all these parameters are taken, and then as I've told you, there's a lot of signal processing that is involved in creation or the formation of this SAR image compared to an optical image. Optical image is slightly straightforward, but for SAR it is not straightforward. You need to do a lot of processing, what you call you need to correct the geometry, you need to correct the radiometry. So all these things happen, and then you get what is basically the what you call the raw image of this particular sensor or the SAR data. Okay, so I hope I'm clear in some of the slides, because I'm not looking at the chat. Probably if you have any questions, we'll take it at the end. So this is again for your information. Probably if you come across the microwave data or the SAR data, and if you're wondering like what each SAR frequency is corresponding to in terms of the frequencies and the wavelengths, probably you can quickly have a glance to this slide, and then you can get to know what are the frequencies and the wavelengths. Okay, so this slide, I think probably it has come in the earlier slide also. This is just to show you like how transparent these bands are to the atmosphere. Okay, whereas optical, it gets all absorbed, scattered, thereby creating a lot of noise. Whereas with the microwave data, it is much more transparent for these frequencies, so that the penetration is also there to observe the terrain. Okay, so again, based on the frequencies you'll get to see different penetration levels, both at the surface and also at the subsurface. Okay, so again, these are prone to what is called as backscattered in different geometries. So if you have a geometry like this, probably you'll get a lot of backscattered. So why this backscattered is important is only if there is a backscattered, you will be able to get a signal. Okay, so if you see water bodies in a SAR data, it mostly looks very dark. Why? Because the surface acts as a specular scattering. That means it's a very still surface. Then you'll not get any signal out of that still surface. So that's why water body in a SAR image is always very dark, and that's why the SAR data is used along with the optical data as a to complement like some of the what you call feature extraction tasks during monsoon days or during any flooded scenario. Okay. Right, so these are some of the distortions that you get if you are using a SAR data, because it's an active data. As you can see here, like there is what I call geometric effects called foreshortening, there is a layover, and there is a shadow. So all these things are basically distortions that are crossed because of the geometry, but all this can be corrected. Again, this is for your information if you are planning to work in this particular domain. So you also need to be aware of what are the different distortions, and now it can be minimized before you start using a SAR data. Okay, so this is so this is basically like some of the data sets that were captured from the RISAT-1 data for different polarization. So different polarization means you'll get different what you call terrain features out of the image. Right, so this will anyway. Okay, so this I'll try to probably, there are different modes. Some of the slides I'll probably rush through because I think we are already short of time here. We have one more component of GIS to be covered. Okay, right. So now we have seen like what is satellite remote sensing, how the satellite data is able to give you a very what you call very wide ranging information from the ground below. and how it can be captured in different what you call optical, microwave. Similarly, LiDAR is also now slowly coming, and in different spectrums, so that you can now make an informed decision as to basically what is your purpose of your study of using the satellite data, whether you are using only for the mapping or for some feature extraction or for some modeling. Right, so you have all this what you call repository of data available in terms of optical, microwave, and also other forms of panchromatic data, and also the frequency at which you are trying to get the data. So all this is probably forms a major input to what is known as solving any what you call spatial problems. Okay, so where GIS comes into picture is now, apart from this satellite data which we are going to get a bird's eye view of the ground below, there are other things also that we need to create. Okay, so what is that? Basically, we also need to understand like how the roads are there, how the buildings are there, right, and how the some of the point data that basically is there. Suppose if you want to capture the traffic signal posts and put it on a satellite image. So how I am going to do that? Similarly, if I want to have that road network information, how I want to put it in my satellite image. So how I'm going to do that? So that is where probably the role of GIS comes into picture. Okay. So in simple terms, GIS, as we all understand, is a computer system that has a software capable of loading this satellite data or the spatial data, and it also helps you to create lot of what you call geometric information, okay, or the shape information like point, polygon, and line. Okay, because most of the real world features or targets that we are living in can be modeled as a simple point, line, and polygon based features. Okay, right. So this is how a simple, if you want to define a GIS, right? But of course, above this, now GIS softwares are become very advanced. They come as a single package, okay, like a database where you can store all the information in it. Once you say it's a database, it has its database features like the integrity of the data can be maintained. You can pool the data based on their what you call coordinate reference system. You can add the different features, you can add different properties. Ultimately, what the aim of GIS software is to see that the integrity of the data, or the what you call the quality of the data is maintained before you start any analysis of that data. Okay, so if you want to answer some simple real world problems, okay, like suppose you take this example of this what you call traveling. If you're traveling to a place, let us say from X to Y, so how long it will take? If you just input these two parameters, it will show you in real time like what will be the time in which you are going to reach that particular destination. So all this basically is generated with the help of the GIS that is running in the background. It takes basically your location. It takes other variables also. Other variables is basically like the other traffic conditions. What is the traffic congestion? So all these things, these are modeled into that algorithm, and then it will be showing you like how it is, what is the solution for that one. Okay. But that is just an example, but much more advanced applications can be developed out of a simple reasoning of understanding the real world problems. Okay. So let us say, for instance, you want to reduce the traffic congestion. Okay, so then what is the solution you are going to offer? So like this, probably if you have a GIS map or a GIS tool in front of you with all that required information, you'll be able to quickly either you can model it by using the different layers, data, or the variables, or you can quickly look at whatever the existing layers are there, and probably then you can, by looking at a map, you'll get to see entirely like what is what in that particular situation. So you can also give very quick solution to those problems. Right, so the GIS, as I told you, like is a tool readily available on the desktop. It's now as a very advanced tool. Now QGIS also has a very advanced set of geoprocessing tools that are, at par with already existing what you call license or commercial software. It is an end-to-end tool, QGIS. Like Sir has also told in the morning, it has a different architecture of handling this plugins. Right, so that is also a very interesting feature. I request all of you to use those plugin tools also. Very useful tools, very handy tools, right? So theory wise, if you see, like GIS basically helps you to, it's a basically what we call, it's a place where you collect all the data sets, the satellite data or the other maps, or whatever these point data you have, line data you have, or any other record data that you may be having as a in a book. So that data can also be converted in the form of a table. Okay. So if you are, let us say, if you are handling a station that is monitoring the outflows, and you, because previously this system of using sensors for monitoring the outflows was not there, but now it is there. So that data can also be converted in the form of a table in an Excel sheet or a Word, and then that data can also be converted with the geo information in it, and then we can use it as a layer. So the idea is basically, once you have all these layers or the data available with you, you can integrate them together, you can visualize them together, so do that what you call geo processing, and we can extract very useful and valuable information that will help us in the overall decision making. Okay, probably this is the objective of why we are trying to use the GIS. GIS gives you different outcomes, different scenarios, like if this is this, if this is this, and then this will be the case. If that is that, then this will be the case. Okay, so like this, you can monitor different scenarios, and then you can try to get the very what you call optimal solution for a particular problem. Okay, so again, the theory, I'll not go into that one. Probably I'll leave this presentation with sir, so that you can leisurely go through. And if you still feel you have any queries, probably you can connect to me and we can clarify that. Okay, right. The main idea behind using a GIS is, as I told you, is we want to understand the real world. Okay, so how do we understand the real world? Is by modeling some of these real world targets with simple geometrical objects, or simple shape objects like point, line, and polygon. Okay, right. So the more scientific you want to do all this analysis, the more what you call pakka information you should have for the objects that you are dealing with. Okay, so if you are dealing with traffic, then you need to have that the vehicular information, like how many vehicles are running on the road, like what is that what is the stages of congestion. Okay, so all these things, probably in a very what you call comprehensive way, if you get the information, it will be that much more easier to model. Okay, so I'm not reading the slides because we are already very close to the session. Right, so you need to understand the difference between a data and spatial data. Data, for all our understanding, is basically the tabular data. Yeah, so sorry, the slides are slightly slower here. Yeah, so data, for our all understanding, is basically the tabular data, but this tabular data, as you can see here, that doesn't make any sense. If I look it in a form of a table, I'll not be able to make what is what. But the same data, if I display it as a spatial layer like this, okay, so it makes much more sense. So this is basically the different the automatic weather stations that are spread across the state. So I get to know, like, each district, how many such locations are there. So our information will, what you call, interpretation will be more precise if you have the spatial data compared to if you have a tabular data. So that is possible in GIS. You can convert the tabular data with the geotagged information into a spatial data and use it for the analysis. Okay. Once you convert into a spatial data, you can see here all the information is captured as an attribute table, and it becomes much more easier to work with the data, to look at the data, to study the data, and also understand what attribute it contains directly on a QGIS. In fact, these snapshots you are seeing are taken from QGIS. Okay, so QGIS, all these things are possible. Yeah. Similarly, the satellite data, it also has the attribute information. The only thing is that attribute information is nothing but the pixel value. Okay, so whatever the reflectance, in case of this optical data, you'll get the reflectance value, and this reflectant value is what for each band is what you are going to use for deriving the information from the satellite data, like how we use the indices or the classification of the image into a map, right? Okay, so when you are working with GIS, probably need to understand what is a geographic data model. Okay, so in what are the various ways it can be depicted, it can be used to captured, stored, and at the same time process. Okay, So geographic data model is that one. Basically, it is an abstract representation of the real world targets, phenomena, or any events with the help of some well-defined what we call geometry that we call it as a point, line, and polygon. Okay. So basically what we are trying to do is we are trying to understand the real world by making simple models of these entities or objects or phenomena or the events so that we can bring it in a GIS environment and we can start working with them, right? Right. So similarly, we have what is known as the geographic data models. We have the raster model, we have the vector model, we have the three-dimensional model that is called as a TIN. Right, so that is what this slide is telling about. Okay, not only that, but it is also important to establish the relationship between different targets. Okay, and this relationship can also be defined in a GIS environment. Okay, so what is this relationship? Okay, these are nothing but simple rules and conditions that a particular what you call entity has to follow. Okay. Like for example, there are driving rules. So if you are driving a car on a lane, you should know okay, which way to go and where not to take a U-turn, where to stop, okay, where to take a left, where not to take a right. So all these things probably they are simple rules that govern basically our traffic. So the same rules can be incorporated in a GIS environment. Okay, so that is how we do a lot of modeling in a GIS, right? So ultimately what we are trying to do in a GIS is bring all the data sets into that QGIS environment, the satellite data, the vector data, the point data, bring everything here, establish the conditions, establish the rules, right? And then what you can do is you can do the processing in QGIS. Okay, so why computer? Because it is powerful, it has powerful processing tools. Not only that, now the GIS have come with advanced processing tools, graphical tools, and also the editing tools, right? Even QGIS has that. Probably in the coming days, you'll also get to understand what are the different editing tools you can use, what are the different graphical tools you can use. So all these things are there. Probably you will get to understand in the subsequent sessions. Okay. Right. So ultimately, as I've told you, we need to derive different outcomes, different scenarios out of a given problem. Okay, you'll not be able to extract only one, but you can extract different outcomes of a GIS problem and help you to see that you make the best decision or the optimal decision. I mean, in tune with the reality. Okay, so if you take a decision that is not matching or not, I mean, helping the reality, then it is of no use, right? Okay, so here also probably you need to understand what are the discrete features, what are the continuous features. Discrete features are basically the places like buildings, roads, or your ATMs, your hotels, right? So all that are nouns are basically your discrete objects. So these discrete objects can be represented in the form of point, lines, and polygons. Okay, so if you want to describe a road network in GIS, you use it as a line, isn't it? Okay, so if you are using the same, let us say a river, where you are also interested in know what is its width and what is the, I mean, basically the flow, then you model the rivers as polygons, because polygon means you need to have some area, you need to have some what you call perimeter. So like this, based on the situation of what you're trying to model, you can bring all these real world objects into a GIS environment in the form of the simple graphical objects called as point, line, and polygon. Mostly whatever is continuous, you will get it from the satellite data or the remote sensing data. Like for instance, your satellite imagery is a continuous data, and whatever you derive from the satellite data is basically it's a continuous data, right? And not only that, you'll also, if you want to describe any natural phenomena, basically you have to depict it as a continuous data set. Okay, so this is the difference between a discrete and a non-discrete, or also known as a field data. Field data is very discrete. Okay, whereas continuous data is continuous, just like the whatever the natural phenomena is there. Okay, so rainfall is a continuous phenomena, temperature is a continuous phenomena, humidity is a continuous phenomena, the terrain or the topography is basically continuous. So all this data you will get as a continuous data, whereas the field data basically correspond to the what you call the discrete data, or the field data correspond to the nouns. You take the buildings, you take the roads, you take the lamp post, you take the traffic signals, ATMs, right? So whatever is, I mean, discrete in nature basically comes under the discrete data. Okay. Yeah, so these are again basically like what all the features you can capture, what are the networks you can capture, how we can basically represent a particular target or a phenomenon or event in a GIS is given here. So this probably I'll leave it to for you to go through the slides and try to understand. Okay, so again, GIS data is it comprises of, it's called a spatial data, it goes an attribute data, and also the metadata. Okay, so we'll see like what a vector model is. Vector model is the what you call the representation of the real world targets in simpler geometrical form, like point, line, and polygon is a vector data. Okay, so if you want to model roads, use them as a line format. If you want to model the, let us say, the bank location, okay, you model them as a point data. Or if you want to monitor the weather station, automatic weather stations in your place, you also use them as a point data. So like this, you can model, or if you want to represent the lakes or the water bodies in your region, you use them as a polygon data. Okay, so that is where the vector model is used to represent the discrete data, to represent the data which is not continuous. Okay, similarly, the raster model is there. That is basically an example of your natural phenomena, all your terrain information, your satellite data, or the what you call the rainfall information. Although you don't directly get the rainfall data directly from the satellite data, it can be derived as a continuous data by using the point data. Okay, and similarly, the 3D data like the uh, the terrain or the elevation, if you want to represent, there are different ways of using the inbuilt geographical formats that will help you to visualize and also capture the elevation information as a 3D data. It is not truly 3D. We call it as a 2.2D or 2.5D. It basically gives a feel as if we are moving through a highly undulating terrain. And apart from this, you also need to, if you're working especially in a GIS, you also need to understand what a metadata is. Okay, so metadata is basically, it's a summary of whatever the data sets you're using. Okay, summary in the sense like who has created this particular data. I mean, who in the sense, what is the origin of this particular data, when it was created, what is the geographical, what you call information that is used, what coordinate system is used, what is the, I mean, accuracy. I mean, not all the metadata has accuracy, but some what you call process data has some accuracy details also. So this is the case also with the raster and also with the vector data, right? And this metadata is especially used for the enterprise scale applications. Okay, so if you are using probably at a department level, it is not required. But if say if you are offering solution to an enterprise for a GIS project, you need to also I mean, understand and define what metadata can be incorporated into your GIS layers. Okay, so that is the importance of metadata, and of course there are standards that govern the use of GIS layers based on the metadata, and that is governed by, we have a national spatial I mean, NSDI we have, that is the National Spatial Database Infrastructure. There's an organization that basically what you call defines the standards, and based on that standards also you can develop your own metadata, so that the what you call the data creation, data storage, and data exchange become that much more easier. So even if you're sharing with, let us say, out of your department, people will not have trouble sharing this metadata or interpreting the whatever the GIS layers that you have created. Okay, so metadata probably is useful from that sense, but otherwise for a regular, I mean, for basically for training, we don't stress too much on the metadata. We only show the properties, and then you'll get to see what the metadata. But if you are doing it, as I told you, at a project level or on an enterprise level, then this metadata standards also have to be followed. Okay. Right. So very quickly moving ahead. Yeah. So this is basically what it contains, who has created it, when it was created, what is the coordinate reference system that was used. So all that summary of that data set that was created can be, I mean, obtained from the metadata. If you go to the QGIS, I think there's a separate metadata also, but you can also see the same metadata by going to the properties of the individual layers. Right. Okay. Yeah, so this is more about the metadata and how it is useful for identification, evaluation, and interpretation. As I told you, like suppose if NRSC creates a particular, let us say, vector data in the form of a road shapefile. So you can see here, like these are some of the what you call the details that you get from the metadata. Okay, so who, when it was created, what is the title, where it has originated, what is the scale, what is the projection. So all this information that basically, even without looking at the original data, probably I'll look at the metadata and then I'll see whether it is relevant for me or not. So probably based on that, I can make a quick call and then start using the data sets. Okay. Right, so this is more about in theory. Probably you can refer to my slides. Yeah, so as I've told you, like we basically model the reality in terms of points, lines, and polygons of the discrete nature of the data because they are also useful. No, we cannot get everything from the satellite data. So there are limitations of what we can derive from the satellite data, but others we can model it using the point, line, and polygon data. Okay. Apart from that, we also have the raster data, which is nothing but the pixel data. We have the elevation data as a can also be represented as an grid, right? So the elevation data can be represented as a contours. Similarly, if you want to represent or convert the same elevation data into a simple three-dimensional way of looking the data, we can also use. So all these tools are available. The good thing is not only the tools, but the formats in which you can use this data and display them in the QGIS are also available, and it can be used, right? Yeah, if you're working with the vector data, especially, probably you have a separate hands-on also, like how to create those spatial features. You should be mindful of what is known as the topology. Okay, so topology in a simple way is basically like observing the relationship between the different vector features. Okay, so how well they are placed among the features, what is they have their connectivity, or what is their proximity, or whether they are overlapping with each other or they are contained in with each other. It's a simple definition, but if you see it practically, topology basically allows us to derive quality vector data out of your project. Okay, so if you are delineating, let us say, a point, line, or polygon, and if you are conscious of not to create many errors like this, the gaps that you are seeing, okay? So instead of delineating from this main, let us say, line, I have delineated only to, I have not joined this line to this main line. So that means that information is missing. Similarly, I have overshooted where I have digitized some of these portions of this 2 that is circled here. Okay. Similarly, when you are doing automatic digitization, there are chances that you may end up with gaps like this. Okay. So these are called as sliver polygons. Okay. Sliver polygons means geometrically they are not well defined. There is a small gap. So this may create errors in your, when you're assessing the area or the perimeter of that particular polygon, you see these will create a lot of errors, and that will in turn affect the accuracy of your project. So these type of errors can also be addressed in QGIS environment. There are again separate plugins available that probably you will also get to see those plugins, how to check that. So topology basically deals with that, and how accurate or what is the how quality data you are producing in a GIS environment when you are digitizing or using the conversion tools. This can be achieved in the QGIS. Okay, so probably again there's some more theory. Probably I'll not go into that one. So how different features can be represented in both the, yeah. So I was actually talking about the advantage of going for a database. Okay. So database makes all whatever the effort that you're trying to create of capturing the data, putting them together, defining that common specifications, your accuracy, your standards. So all these things can be done much more what you call confidently if you have a spatial database. Okay. So that is where the spatial database or a geodatabase, if you have, some of you have used ArcMap, will appreciate that one. So that is where the geodatabase concepts have really come in now, and mostly people are working in that same format. So this will make a lot of things much more easier compared to if you use a standalone GIS layer. You can put them in a, because any project of GIS basically comprises of multiple GIS layers. Okay. So where you'll be working, as I've told you, look, plenty of layers. You need to first capture it. You need to put it in a geodatabase, and then you can create whatever the analysis that you want to create. Okay. Right. So the geodatabase formats have also evolved. So it was called as the georelational model, but now it has come to a spatial database format, where the actual behavior of certain targets or features or entities can be modeled in a similar manner in a geodatabase. Okay. So this, like, suppose if you have a flyover running over that one of the roads, so how you model that one? Okay, so you can say, like, you can create a subtype of that flyover, saying that this is a flyover, or this is a underpass, or this is an overpass, or like this. You can create a subtype of that main feature, and you can work with that in a geodatabase environment. Okay, or in a spatial database environment. QGIS does support what is a package called as a geo package. It is almost similar to a geodatabase, but the implementation of this geo package needs some understanding. Okay, so probably you need to explore what are the features and what are the what you call specs of this geodata package, so that it can be used to model the real world behavior of certain entities or objects. Right, so this is again some more theory of spatial database and why it is needed, especially, as I've told you, like if you're in handling a GIS project, it is better to put them in a spatial database rather than working as a standalone what we call GIS layer. Because with the geospatial database, all the features of a database comes into picture. Okay, what I've told you, like the data integrity or the data correctness, or the what you call the basically accuracy also can be maintained if you are working with a geodatabase or a spatial database environment. Right. So quickly further going. So this is how the database is implemented in a geodatabase model. Again, this I leave it for your going through. And similarly, GIS and begins with and ends with the real world. I think this is a very what you call a relevant statement that is made, but again I'll skip through. Okay, so typically any GIS project involves a lot of workflows, right? So you need to create what is the starting point, what is the inputs, what are the other parameters that need to put. So typically the workflow environment is what is maintained, especially if you're modeling with the GIS layers. Okay, so all these slides probably I'll rush through because we're already yeah. So this is where we combine different layers of different types. So if you monitor, let us say if you want to do the hydrological modeling using a watershed, right? So you take the elevation data and then you use the hydrological tools in QGIS to first derive what are basically the different channels, different orders of the what you call the channels, and then you create a simple hydrological watershed model like this. So this can be done in QGIS also. Okay, right. So all this stuff probably for your information. I mean. I'll not go through this because probably I've given you what is the gist of why we use for GIS. Okay. Yeah. So what are the different data sources that we have seen? Like the remote sensing probably forms the primary source of the data for the GIS. So you can do it from the ground surveys. If you already have some old topological maps available with you, or topographic maps available with you, you can scan it and also make use of those maps, right? So you can get the data from the aerial platform or from the ground. As you can see here, like the navigation data is also very important. We can use any data that is basically corresponding to the real world into the GIS, and we can start working with them. Okay, so these are some of the major sources. Right, and data conversion also plays a very important role. Probably you will get to explore in this training program, like how the data can be converted, as I've told you, from point to spatial data, how it can be converted. Similarly, if you have a what you call physical copy of a map, how we can scan and convert and put it into a GIS layer. So all these things probably you will get to learn in this particular training program. Yeah, so again, there's a lot of things probably in theory. You can do this many type of analysis. You can do descriptive, explanatory, and predictive analysis in GIS. Again, I'll not go into that one, right? So basically, you have what is known as a querying option, provided you have all the information as GIS layers available. What you can do is you can do it with a simple query using our natural reasoning of how basically we identify. Like this is just like if we go for a shopping, which one will suit us the most. So this is simply like using a software to get that optimal what you call product or a service by using a GIS. So if you already have a database and if you are looking at a specific what you call what you call target or a specific feature from the database, probably you can use a simple querying. Okay, so you have all your wish list or the conditions based on which you want to find out. So similarly, you simply do a querying and you'll get the output. Okay, similarly, you'll also get to see what are the different trends. Okay, so this is what we do in the what you call the change analysis and how the city has exploded or grown, right? And similarly, the patterns. Okay, so if you understand the patterns of let us say a particular event, okay, like there is a particular place where the accidents are more frequent, so you'll get to see what are the patterns, and based on the patterns you'll get to observe what is basically causing those events in that particular fashion. So we can find out those patterns also. Okay, right. Similarly, the topology, as I've told you, like will help you to identify basically the what you call the gaps in your data sets, and it will also help you to identify the features that you are interested in. Okay, and similarly, modeling also you can do it with the help of what you call a graphical model is there, but that is more of very straightforward. But you can do very complex modeling also in QGIS environment, right? And of course, the analysis part, as I've told you, like this is basically the what you call the brain of this QGIS software. So this is basically the different tools that you get in a QGIS software. You can see here like they are neatly categorized under various headings. Okay, so you can you can derive the data, you can extract, of course you can use it for your interpretation or inference, you can model it. There's a separate graphical modeler in QGIS. You can also validate the data provided you have some what you call ground truth information or a reference information, and you can also publish readily as a GIS layer. Okay, so that is the advantage of using a QGIS software. The data is now what you call GIS ready, and you can share it with your what you call your fellow fellow officers, or if you want to publish the data as a service, that also you can do it, provided you need to have a separate what you call geo portal for that one, or a server basically that stores the data. So all these things are possible in a GIS environment, provided that you do the analysis. Okay, and these are typical workflows. Again, I'll not go into the details of this one, but all these things are possible in a GIS environment. Of course, this I've taken from an ArcMap just to show you like what are the different types of inputs basically go into the analysis of the GIS data. So probably you can have it more what you call detailed look into that one into the once you get this presentation. Okay, right. So once you analyze the data, once your data is ready for sharing with the users or your with the people, then they can be used to showcase the same data using geoportals, or they can be captured as a web map services, and people can use the same data. I think the web WMS services are more popular now with the QGIS, so that also you can use it. And especially if you are want to create a decision support system, this is where also the GIS plays a very prominent role. In that it basically creates is basically the what you call the cornerstone of this decision support system. So we have some we have also developed some decision support system like the emergency database management system and the cadastral mapping system. So this is basically an independent system that is floated on the web, or I mean given access to some what you call authorized people, where they can clearly visualize the outcomes of a particular event. Okay, so they can, like suppose if there is a heavy rainfall event, and how that how the event is progressing can be monitored using the decision support system. So there's an end-to-end automated system where all the decisions are already incorporated into the programming or the design of the system. So you get to see only the what is the real-time data and also the outputs from the decision support system. And of course, we can also share it with a ministerial, like ministry or a nodal agency, which is sponsoring a particular project, and you can update them with the whatever is happening, like with the project. Okay, right. So these are some of the dissemination platforms where we can share the data of the GIS, right? And of course, also the remote sensing data. Okay. Yeah, so probably this is where I conclude my presentation. So these are some of the references. I think most of the information is already there on the public domain. So probably you can also, if you're interested in a particular subtopic, probably I recommend that you can explore it. It is already there in the web. Probably some of these slides also will help you to to try to get a fair and a thorough understanding of what GIS actually is. So in summary, that is what I have to share with, especially from the remote sensing and also the GIS point of view. Remote sensing is the primary source of the imagery that you get to work with in a GIS data. But as you have seen, like GIS also need other forms of data sets like the like the discrete data, like the road data or the point data or the live polygon data that you need to combine in a GIS environment, and you can use the layers for analyzing, doing the spatial analysis and deriving the solutions or the outcomes from that layers. So this is all from my side, ladies and gentlemen. Thank you for your valuable listening. And if I have probably if I have questions from your side, I'll take. Sir, over to you, sir. Chaitanya.
Yeah, thank you. Thank you very much for delivering a very comprehensive presentation on giving an overview of GIS and remote sensing technologies. There is one query in the chat box on whether we can process SAR data in QGIS. Can we do it?
Yeah, yeah. Actually, SAR data processing is slightly more complicated in QGIS because it also depends like what is the sensor data you are using. So if you are using our Indian data sets, or if you are using, let us say, the foreign data set like Sentinel-1, so there the process is slightly more complex. So I recommend that if you are using, let us say, a Sentinel data or a RISAR data, there are separate what you call application tools that are available that will allow you to do that what you call the pre-processing of the data. Okay. If you are using, let us say, RISAT1 data, there is a separate tool that you can also download where you can do the pre-processing of the data if you are using RISAT data. And similarly, if you are using, let us say, Sentinel-1 data, there is a separate tool called as the there's a separate tool. I'm not able to recollect that one. So you can do that pre-processing, and then for the feature extraction part, probably you can use QGIS. Although there are pre-processing tools are available, but they are slightly more complicated, because what we need to understand with the SAR data is the metadata and the processing parameters that come with the metadata also basically are taken in for the pre-processing. Like for instance, if you are converting it or doing the radiometric calibration, then you need what are the different what you call the gains, the coefficients, and all those things, parameters will be taken into account, and then the pre-processing takes place. Whereas in a QGIS, you need to basically understand each and every input parameter, and then probably you have to give the input for the processing. So at the moment, with whatever understanding I have as far as the QGIS environment is concerned, it has pre-processing tools, but they are not in a user-friendly mode. So what you do is you take the data, do the pre-processing in the what you call recommended application software tools. Okay, yeah, for the Sentinel data, it is called as a SNAP. Okay, SNAP, you can do the pre-processing. Similarly, for RISAT data, there is a separate application tool, and it is also there in probably I'm not able to recollect. It is also there in the another license software, but pre-processing you do it in those softwares. Probably for feature extraction, you can use the QGIS.
Okay.
Yeah, I hope I've answered your question.
Yeah, now the participants can unmute themselves if they have any query. We will have only 5 minutes of question and answer session. And if you have further any queries, you can post them in the course forum, or in the evening, we will meet again at 5 to 6 p.m. for queries. Now, let me tell you that this is a very foundational, it is designed to be a foundational training program, a basic training program. But however, we have diverse set of participants. Some of the participants are doing their master's degree, and they may be working on some project, so their requirement may be at a higher end. So if you have such queries like processing of SAR data, etc., that we may not be covering during this training program, which is about the basics of GIS and RS technologies. But you can definitely post your queries. We will pass them on to the guest faculty, and we can get back.
Can you explain about the metadata? Metadata, how it is different from a spatial data?
So metadata is what you get to see in the form of the specifications. So just like if you buy any product, so what we do is on the boxing, we'll see what is the specification. So even before we open in that particular, let us say box, if you go to the specification, they'll tell you, like if you are buying a mobile phone, it will tell you that this is a 16 GB RAM, it is a 256 GB ROM, it has so and so megapixel. So basically that is what metadata conveys to you. So even before you look at a particular layer, if you look at the metadata, it will give basically what is what of the data, like what is the origin of the data, who has created that one, whether it's agency has created it, whether it's an individual who has created it, when it was created, what was the purpose of creation, at what scale it was created, what is the spatial reference system or the coordinate system that was used. Okay, what are the applications it can this particular layer can be used. So without actually opening the data, just by looking at the metadata, I can probably understand its relevance or the utility of that particular layer for my GIS application. So that is what the importance of metadata is. But for a standalone user, like if you are working for a standalone projects, you may not appreciate the value of metadata. But as I told you, like if you are working at an enterprise level, where you have to, let us say, map the entire Hyderabad city using the satellite data, create the road network, create the drainage network, create all the parks, create the schools, buildings. So if that scale, if you're trying to generate a GIS project, you have to maintain certain metadata standards. And that is what also I have shown in one of the slides, like the metadata is also governed by the NSDI standard, which is a National Spatial Database Infrastructure Standards. Okay, so that is important, sir.
Okay, thank you.
It basically allows you for easy creation, storage, and also the sharing of the data. If you develop a proper metadata standard for that one.
Thank you.
Sir, can you please explain the term that active and passive?
Yes, sir. Active is basically if you are like, suppose if you are aware of this LIDAR. Okay, so what the LIDAR does, it basically sends pulses of the laser light. Now this LIDAR technology is used to also what you call map the archaeological sites. Okay, so we call this as a terrestrial scanner, laser scanner. So active sensor or active technology basically uses its own light sources. Okay, it uses some frequencies of laser pulses or in the visible or in the microwave region, and whatever the echo or whatever that backscattered portion of energy is reflected back is captured, and it will be processed and then converted into a three-dimensional image, like how we get in a what you call a 3D scanner. Okay, in a 3D image, how we'll get to see everything in three-dimensional. So that is the example of an active sensor and active technology. Whereas a passive technology is basically like your mobile camera. So what we are doing in mobile camera, just you are looking at that target and just taking a picture. So we are getting an image of that one. So that is what the example of passive technologies. So passive technology basically use the surrounding lights or the ambient light to capture the information. Whereas in active technology, we are actually using the source from the light sources from the platform itself to derive that 3D information or the 2D information or whatever information is there on the ground. So is that clear, sir?
Yes, sir. Yes, sir. Thank you.
Yeah, from a remote sensing point of view, you noted like optical means passive. If you are working on the optical data, it is a passive technology. If you are working on a SAR data, it is an active technology. Or if you are working on a LIDAR data, this is an active technology.
Then in the chat box, there is a query on sources of downloading satellite imagery. So we will be having one session on open source spatial data sets in the afternoon. So I think that will answer the question. And about the specific question on how to get DEM data, which is less than 30 meter spatial resolution, I think that can also be, that is not freely available. Mr. Harish can correct me. But that can be ordered in using the Bonidhi portal, and you have to make some payment. At 30 meter resolution, it is freely available. We will see in the evening session how to download it.
Even that 30-meter data can be downloaded from the USGS portal. So you have the Aster Global DEM is there, so that you can download any number of tiles of the entire Earth. But that again is available at 30-meter coasting. But for better than 30 meters is always a challenge with the DEM data. Okay, so probably that is where your LIDAR are slowly, I mean, a lot of players that are promising like they can derive the sub-meter, elevation models are now, so we can give probably a partner with them for the, so they'll do the flying and they'll using that photogrammetric techniques, they'll extract the elevation data up to 1 meter.
Do we have DEM data which is less than 30 meter with NRSC? I think it is there, but it is not freely available, right?
Yeah, it is there, sir. As you rightly told, like we probably distribute them on some what we call some understanding basis, on some MOU basis. I think we have some 10-meter CARTOS DEM also, but again, it is not freely available. If you are working on any project that requires such accuracy and you want to basically partner with NRSA, so probably on an MOU basis, we can share those tiles with you.
Sir, it is also UAV drone survey in supporting to QGIS, or they have need any other software, special software?
Sir, at the moment, now that is an emerging technology, sir. The drone technology is emerging. So now what the what you call the providers are giving is, so they are giving their dedicated software to process this drone data, right? So there are also open source tools that you can use it to process this drone data. But from my understanding, what I'm seeing is like there are dedicated softwares that are provided with the drone data also. There are open source tools also like QGIS also. There are separate tools are available that are useful for processing the drone data. But now just to enhance our understanding, if we directly start with working with this open source tool, probably you need some background and also some what you call experience in this particular domain. Only then you will be able to use that drone data. But otherwise, what I've seen is like they come with a dedicated software that will allow you to basically download the data, process the data, do some analysis on the data, and also derive maps out of that one. So at the moment, the situation is like that. Probably in the coming days, just like with QGIS, how it has changed in the last, 1 decade, we can hope that the similar thing happens with the drone data also.
Then there is a very basic query
Are
regarding what
Bhuvan,
is.
NRSC and Q
You are not clear, Mr. Shivaraj.
Sir, are the Bhuvan NRSC website and the QGIS are interrelated or what?
No, sir, they are not interrelated. Bhuvan is our geo platform of India, where all the not only the satellite imagery but the thematic information, the weather information, the disaster information, and a lot of application projects of national importance are being hosted in that geoportal. Okay, so it's a one-stop shop for all the geospatial information that you want to get from of our Indian region. So you visit Bhuvan, then probably you will get a better understanding of what data it contains, what visualization feature it contains, what data can be downloaded, and what simple GIS tools are provided. So all this basically given as a part of for the public. But whereas a QGIS also, we can explore some of these data sets as what we call as a map or as a service by from the Bhuvan Geoport. So I would say that they are not directly related, but if you want to visualize some of the data in the QGIS environment, you can also do it using the QGIS software by using the web map services of some of our Bhuvan applications. Okay, especially the thematic services, no, like land use, land cover, or the geomorphologic map. If you want to visualize in a QGIS environment, you can call that as a web map service, and you can see what are the different layers and what is the information contained in that one.
Okay, sir. Okay, sir.
Okay. Okay, then I think we can conclude the session. If
Sir,
there
I
are.
have one question,
Yeah.
if you allow me,
Yeah.
sir.
Yeah.
Sir, what is this GDB data, geodatabase? How is it different from like shape files?
Yeah, as I told you, sir, like now the concept of geodatabases or various formats of the same spatial databases are now coming into picture, because it gives you that much more flexibility and the confidence to work with the GIS layers. Okay, so as I told you, like if you're working with, let us say, dozens of GIS layers or more than that, if you are trying to analyze or do some what you call information extraction from all these layers, a simple GIS layer is not going to hold, good for the remainder of your project. Okay, especially if you want to share these data sets to your, suppose you have, let us say, multiple locations in the country where you want to share the data. So if you do it as a geo database, it will be that much more flexible. So now these geo databases can also be hosted in the cloud. Okay, in fact, the QGIS also has a cloud, as a resource now. So what you can do is, once you put everything in a geo database in a cloud, the same cloud can be accessed by the rest of the users who are working at different locations, so that you can share them in a matter of very quickly, in a matter of time. You can also get their feedback. You can also implement those some of the suggestions in that feedback. So in a very comprehensive way, we can work if we have a geo database format.
Okay, sir. Thank you.
And it has its own advantages. Probably I have not elaborated in during this session. It basically allows your spatial integrity of the data, the accuracy of your data, right?
Okay.
So once you define, let us say, some of the what you call the values or the parameters or the conditions of your geo database, that will hold till the project is concluded. After the project has also concluded, the same values will hold good for all the layers. Suppose if you have, let us say, 50 layers in your database. So all those layers will be governed by whatever the conditions you have defined for the database. Apart from the integrity issues, what you call advantages that I've told just before.
So both raster and vector layers can be.
Any raster, vector, point, polygon, line data, if you put it in a geo database format, it is that much more easier to work with.
I think
Okay? But the only point you need to note is the implementation of this geo database in QGIS is slightly different. Okay, because I have also worked in the geo database of the ArcGIS ArcMap. So there the implementation is slightly different. The geo packages is slightly different. So probably you need to get used to or understand what are the other things you need to note or put in mind before you start using the geo database. But for a learner or an individual standalone GIS layers, I think you can directly use them as a layer. Okay.
Right.
But if you are doing it in a more comprehensive or a slightly bigger scale, it is recommended that you go for a spatial database or a geo database.
Okay, sir. Thank you.
Is it possible to background use image as a satellite image of ISRO, like web map services?
It is possible, sir. So probably, I don't know. Chaitanya garu, you have that QGIS web map service in that session?
No, we haven't included, but we will cover them to add how to add basic maps using the plugin the publicly available base maps of Google and OpenStreetMap. That we will cover.
Yeah, fine, sir. Yeah, you'll get to understand, sir. It is available in QGIS.
Okay, then I think we can conclude the session. Thank you very much, Shri P. Harish, scientist SF from NRSC, for delivering a very comprehensive session. It is very helpful for our participants. You can share the PPT with me, and then I will be sharing with all the participants so that they can go through. And if there are any queries, I will post them to you so that I will.
Sure, sir.
Yeah. Thank you very much. We will
most
have.
welcome, sir.
Yeah, we will be having the second session at uploaded. It will be uploaded at 2 o'clock after lunch period. We will have two sessions today: introduction to QGIS and how to install the software on your systems, and then there will be a very comprehensive session on open access data sources, various data sources which are publicly available. We will see it at 3 o'clock today. So thank you very much for joining us today. Hope to see you after the lunch period, and we will also have a question and answer session from 5 o'clock. Once you cover all these sessions, the second and third session at 5 o'clock, I will be sharing the link afterwards. Thank you.
Okay, sir. Thank you. Thank you for the opportunity, and all the best to all the training officers. Thank you.
Thank you.
Thank you very much, sir.
Thank you so much, sir.
Thank you, sir.